All right, last bit of information about exponential and logarithmic functions before we move on to trigonometric functions is let's talk about solving these kinds of equations, okay? So we've taken a look at the graphs of these things, we've taken a look at some applications for them and so forth. We've talked about how to manipulate logarithms quite a bit, but let's talk about how to solve equations. Exponential and logarithmic equations. So here we go. To solve an so what you have to understand is that exponential and logarithmic expressions undo each other. So if you want to undo an exponential, you take a logarithm. If you want to undo a logarithm, you exponentiate. Okay. So to solve an exponential equation, we isolate the exponential term and then take a logarithm of both sides of the equation to clear the equation. So for example, in part A, we have 3 to the x equals 243. The exponential term is already isolated, so we're ready to take a logarithm. And the logarithm that you want to take is the logarithm whose base matches the base that you're given. So in this case, I want a log base 3 of 3 to the x equals log base 3 of 243. And now we have that property of logarithms that said log base something of the same number when the base and the argument match, then those things just cancel off and they leave you with the exponent, right? So we get x equals log base 3 of 243, whatever that is, right? Well, we'd ask ourselves 3 to what power equals 243? I'm pretty sure this is a, so what is it, 3 to the 5th maybe? Yeah, 3 to the 5th, so x equals 5, right? Or if you want to give it, when we say solve, we say find the solution set, right? So really our answer should be a set. So there's our answer. Okay, and that's really all there is to it. Part B, we would take a log base 2 in order to clear that exponential. So we're going to take log base 2. So we get x equals log base 2 of 9. Now, in order to do log base 2 of 9 in your calculator, you would do ln of 9 divided by ln of 2, right? Most of the time, I want the exact answer as well as a decimal approximation, so just get into the habit of giving me both. So let's see, ln 9 divided by ln 2. That's about 3.170 if we go to 3 decimal places. So anyway, our solution set would be log base 2 of 9. If you want to give the, maybe if you want to give the approximation, you could say it like this, log base 2 of 9, which is approximately 3.170. Okay, let's do part C. Now in part C, we have to do some isolating first. We can't just take log base 4 now, because if we take log base 4 now, we're not going to be able to distribute it to the -7, right? So if our goal is to get this exponent down, then we need to first isolate the exponential term, and then we can take log base 4 of both sides. So I'm going to add 7 over to the other side. Then I'm going to take log base 4. Here the log base 4 and the 4 cancel. You get ln 12 divided by ln 4. Although you're still not finished solving for x, so maybe I'll just leave it. 2x minus 3 equals log base 4 of 12. Because we still have to solve for x, right? So at this point, now we need to add 3. And then divide by 2. And don't you dare call this log base 4 of 15, right? You have to take log base 4 of 12 first before you do the addition. So it's really, this is what we're really talking about, right? Anyway, It's not the same thing as log base 4 of 15, okay? But then we divide by 2. This is our exact answer. Now, if we want a decimal approximation, we can say, now I'm going to have to do my change of base, ln 12 divided by ln 4 plus 3 divided by 2, right? And then I can punch that into my calculator and see what I get. So that's about 2.396. Okay, so our solution set would be log base 4 of 12 plus 3 divided by 2, which is approximately 2.396. Now, before we go any further, let me just say, you don't have to match the logarithm with the base of your exponential. You could take any logarithm and that'll allow you to pull the exponent down. So let me show you this one again. 3 to the x equals 243. Since you know that you're going to have to do a change of base anyway to punch the answer into your calculator, you could just start off by taking ln of both sides instead of trying to match the logarithm with the base. And that's perfectly legal. The only thing you have to remember is that these things don't cancel now. What happens is you use the power rule to bring the exponent down. So you get x times the ln of 3 equals the ln of 243. And then to finish solving for x, you would have to divide by ln 3, right? So you get x equals ln 243 divided by ln 3. And if you punch that into your calculator, you're going to get 5. Right? ln 243 divided by ln 3 is 5. Maybe an even more convincing one would be part B, because look at part B. Instead of matching, so solving this again, instead of trying to match the logarithm, log base 2, you could just take ln, then bring the exponent down, and then divide by ln 2. So x is ln 9 divided by ln 2. Well, look, that's exactly what you had to do in order to punch it into your calculator anyway, right? So so a lot of times, especially in calculus, we kind of prefer to solve exponential equations this way. You're welcome to do it either way. It doesn't bother me. However you want to write it out is perfectly fine. The only time that this becomes maybe a little bit more cumbersome is when you're solving things like part C, right? Because then you have to carry more symbols around from one step to the next, because you're carrying this expression around instead of this slightly more simple one. But whatever you prefer is really fine, okay? Oh, I have more. I didn't even realize I had more. Let's do it. Let's isolate the exponential, and then we'll take a logarithm. So I'm going to add 2. Remember, 7 times 3 to the x plus 1 is not the same thing as 21 to the x plus 1. They are not the same. But also, I haven't finished isolating my exponential. I need to divide by the 7. Now I can take a logarithm. If you'd like, you can take log base 3. Otherwise, you can take ln. I think I'm going to take the ln. So I'm just going to take the ln at this point. So I have x plus 1 divide by the ln of 3. And then subtract 1. I don't know why I put parentheses there. It's not totally necessary. And there you go. That's that solution. To see how much this is, you can punch it into your calculator. What was it? 3 ln 3 minus 1 So ln of 11 over 7 divided by ln of 3 minus 1 is negative 0.589. Right? Negative 0.589. Okay. That's that one. Part E. Oh man. See, now this one, if you were trying to solve it by taking the logarithm whose base matches the exponential, it would be a little confusing, right? Should you do a log base 3 or a log base 2? So, so for this one, definitely just kind of doing a neutral logarithm, like natural logarithm, would probably be a little better. So I'm going to take ln on both sides. That's going to allow me to take the exponents down in both cases. I've got x plus 1 times natural log of 3 equals 2x times the natural log of 2. Now I have to finish solving for x, and here's where things might get a little tricky. What I'm going to do is I'm going to go ahead and distribute this ln of 3. So we're going to have ln 3 times x plus ln 3 equals 2 times the natural log of 2 times x. Right? And I'm just writing it in this kind of funny way with parentheses to emphasize that ln 3 is just a number, right? It's just a coefficient. So this is something times x plus something else equals something times x. Now, if you think about how you would go about solving that typically, you would try to get your x's on one side and get your numbers on the other, right? So I want to move this ln of 3 over to this side, and I want to move this 2 ln 2 of x, or 2 ln 2 times x to the left-hand side. So I'm going to get ln 3 times x minus 2 ln 2 times x equals negative ln of 3. Now I can factor out an x. I get x times ln 3 minus 2 ln 2 equals negative ln 3. And to finish solving for x, then I just divide by this coefficient, right? So I get x equals negative ln 3 divided by ln 3 minus 2 ln 2. That's my exact answer. Let's see about how much that is. Whoops. So that's about 3.819. Okay, so there we go. So that's that. Okay, so that's the strategy for solving an exponential equation. Let's talk about solving logarithmic equations. So it's very similar, a very similar process, right? To solve a logarithmic equation, we isolate the logarithm, and then we exponentiate by the base of the logarithm. Okay? In order to isolate our logarithm, sometimes we have to use a product or a quotient rule. And then the other thing that we have to check for when we're solving logarithmic equations that we didn't have to do when we were solving exponential equations is that we have to check our solutions to make sure that they yield positive arguments. Remember that the argument of a logarithm has to be a positive number. So we need to check our solutions to make sure that the arguments are positive. And if they make a negative argument or a zero argument appear, then we're going to kick them out of our solution set. Okay? Let's look at a few examples. So step 1, isolate the logarithm. Step 2, exponentiate. Exponentiate. using the same base as the base of the logarithm. So in this case, since this is a log base e, we're going to exponentiate by e. What I mean by that is we're going to not raise both sides to the e power. We're going to do kind of the opposite of that. We're going to say e to the ln of x equals e to the 3/2 power, right? We're exponentiating, right? The only way this statement is true is if this statement is true, right? So it follows. And now what happens is that the logarithm and the exponential cancel, leaving you just with the exponent. So you get x equals e to the 3/2 power. So there you go. There's your exact answer. If you want, you can figure out about how much that is. E to the 3/2 is about 4.482. Okay. I cannot tell you how common it is for students to make the mistake of trying to solve a logarithmic equation by taking a logarithm. It's not going to work. Exponentials undo logarithms. Logarithms undo exponentials. Logarithms do not undo themselves. Okay? So you don't take a logarithm to undo a logarithm. You exponentiate to undo a logarithm. Okay? Just like in order to undo an exponential, you don't exponentiate, you take a logarithm, right? Okay, let's look at part B. Part B is kind of interesting. We've got so many logarithms happening here. If we exponentiate now, it's not going to turn out well for us. We've got to use a product rule to combine these two logarithms before we can move forward, I think. So I'm going to use a product rule and say log base 4 of x, I was about to use the quotient rule. It should be the product rule. X plus 5 times x plus 1 equals log base 4 of x minus 1. So you get log base 4 of x squared. X plus 5x is 6x plus 5 equals log base 4 of x minus 1. Now I'm going to exponentiate, this time by 4. Okay. 4 to the log base 4 will cancel, leaving just the x squared plus 6x plus 5. 4 to the log base 4 will cancel, leaving just x minus 1. And now to finish solving this thing, we've got to move everything over, factor, and then apply the zero product property. So moving the x over, I get x squared plus 5x, and then moving the 1 over, I get plus 6. That's kind of trippy. But nonetheless, that is correct. Now we factor this thing. I think x plus 2 times x plus 3 will do the trick. And so then we get x equals -2 or x equals -3. Now don't forget, like I did in part A, but don't forget you have to check your solutions, right? You have to plug these in back to the original equation to see if it makes any of the arguments negative. So if I plug in -2, here I get -2 plus 5, that's 3, that one's okay. But here I get -2 plus 1, which is -1, and that's bad, right? And this one's even worse. So -2 won't work. And for that matter, -3 won't work either. So the only two possible solutions were -2 and -3, but they're both extraneous. They make for nonsensical statements up here. So that must mean we have no solution. All of that work for no solution. Well, I mean, but that's still good information. At least we know, right? At least we know that this thing, there are no real numbers that are going to satisfy this equation. Okay. Let's do another one. By the way, if you check this one here, it's going to work. It's going to be fine, right? When you plug in e to the 3/2 power, you have a positive argument. So this solution is perfectly fine. But let's talk about part C. So again, with the product rule, right, we're going to say log base 3 of x minus 8 times x equals 2. So this is log base 3 of x squared minus 8x. Now I'm going to clear the logarithm by exponentiating, this time by 3 since the base is 3. That will undo that. We get x squared minus 8x equals 3 squared is 9. Now move the 9 over. And factor. So x equals 9 or x equals -1. We've got to check these. So checking 9, here we get an argument of 9 minus 8, which is 1, so that's okay. Here we get an argument of 9, so that's okay. So 9 is going to work. If we plug in -1, -1 minus 8 is -9, that's bad, right? Automatically, that's not going to be any good. So my solution set is just 9. Okay. Of course, you can verify that that actually gives you a true statement. When I was plugging this in, I was just making sure that the arguments weren't negative, but obviously it should also make a true statement, right? Like if we plug in log base 3 of 9 minus 8 plus log base 3 of 9, is this in fact equal to 2? It should be, right? Log base 3 of 1 is 0, right? 3 to the 0 power equals 1. Log base 3 of 9 is 2. 2 squared is 9. And 0 plus 2 equals 2 for sure, right? So that verifies it. You don't have to actually do all this work. You really only need to make sure, like I said, that the arguments are non-negative, positive, right? Positive. Okay. One more. This time we're not going to be using the product rule because we're not adding, we're subtracting, right? So we're going to use the quotient rule. We're going to say, well, this is log base 2 of x plus 4 over x plus 3. And then we're going to exponentiate. X plus 4 over x plus 3 equals 2. So you see all of that work we did reviewing how to solve quadratic equations, how to solve rational equations. It's all coming back in chapter 3, right? Anyway, we solved this by clearing the fraction by multiplying both sides by x plus 3. And then the rest is history. So I'm getting x equals -2 as my possible answer. To check that, I plug it back in here. -2 plus 4 is +2, so that works. -2 plus 3 is +1, so that works. So this is a good solution. So as you can see, it's not that the solution isn't allowed to be negative. The solution could be negative. It's just that when you plug the solution in, it can't force any of your arguments to be negative, right? That's the trick. But -2 is fine. It's a perfectly good solution. Okay, so that's how we solve logarithmic equations. Now, let's take a look at some applications of this. So number 3 asks, how long will it take to double your money if it earns 6.5% annual interest compounded continuously or compounded monthly? So 2 different questions that we have to answer. So remember back in 3.1, we talked about compound interest. The formula for continuously compounded interest was P equals P naught e to the RT. For compound interest that was compounded in a finite number of times per year, we would use P equals P naught times 1 plus R over N to the NT. So there are 2 different models, but let's see if we can answer the question, okay? We don't actually even know how much money we're starting with, but we just want to double our money. So it actually doesn't matter because whatever the initial amount is, the final amount needs to be 2 times that. So if our initial amount is P naught, then our final amount is going to be 2 times P naught. R is 6.5%. And T we don't know. T is what we're trying to solve for. Okay. Notice I can get rid of the P naught unless P naught is 0. If P naught is 0, then of course it's impossible to say how long it'll take to double, right? Twice of 0 is 0, right? 2 times 0 is 0. So anyway, but we get the statement 2 equals e to the 0.065 t. This is an exponential. How do we solve an exponential? Well, we isolate the exponential, done, and then we take a logarithm to bring the exponent down. So I'm going to go ahead and do that. Take the natural log of both sides. So ln2, the ln and the e cancel, so that's going to leave me with 0.065 t. And now to finish solving for t, I would divide by 0.065. So t equals ln2 divided by 0.065. Now about how much is that? Let's plug that into our calculator and see. So ln of 2 divided by 0.065 is about 10.664. So how long will it take to double our money? About 10.664 years, so like 10 and a half, a little more than 10 and a half years. Okay. So there you go. What if the interest is compounded monthly? Well, so then we're going to use this formula instead, and we're going to say, again, we don't know what our initial amount is, but we know that our final amount needs to be twice the initial amount. So I'm just going to use 2 times the initial amount for our final amount. R was 0.065. N, well, if we're compounding monthly, then N is 12, right? And T we don't know. T is what we're trying to figure out. Excuse me. So once again, the P naughts cancel. We get the statement 2 equals 1 plus, actually, maybe I can plug this into my calculator. I don't know, 0.065 divided by 12? No, that's not a very nice answer. So I'm just going to leave it. I'm just going to leave it in its sort of long form, 0.065 over 12 to the 12t. Now, if I want to get this exponent down, I'm going to take a logarithm. So I'm going to take the natural log of both sides. So ln2 equals 12t times the ln of 1 plus 0.065 over 12. Now, I want to solve for t, right? So I need to finish by dividing by 12 to get rid of that 12, and ln of 1 plus 0.065 divided by 12. Let's get rid of that, right? These things will cancel, these things will cancel, and just leave me with t. If I do that on the right-hand side, of course, I've got to do that on the left-hand side. 12 ln 1 plus 0.065 divided by 12. So that's kind of messy, but here's what I'm saying. So the exact value for t is ln of 2 divided by 12 times the ln of 1 plus 0.065 over 12. So there's my exact answer. Now, if I want a decimal approximation, I can plug that in, right? So I can say this is going to be ln of 2. My dogs are going crazy because the mail just came. Hold on. Sorry, I had to straighten my dogs out. So ln2 divided by 12 times the ln of 1 plus 0.065 divided by 12. Oh goodness. How many parentheses? Do I have all the parentheses in the right spot? So I've got this out one, and then ln. Okay. Yeah, that's right. Okay, so that's about 10.693. So a little bit longer, not very much longer, right? But a little bit longer if it's compounded monthly versus being compounded continuously to double your money. That's the idea there. We've talked in the past about how population growth is also modeled by exponential functions. Another thing that's modeled by exponential functions is radioactive decay. And one of the things that's used to measure radioactive decay and how fast a radioactive substance decays is the half-life of the substance. And this is kind of a tricky concept at first. So let's walk through it, okay? The half-life of a radioactive substance is the time it takes for half of the substance to decay. Which may lead you to think, okay, so let's say it takes 5 years for radioactive substance, for half of a radioactive substance to decay. Then it takes 10 years for the whole thing to decay, right? But that's not correct. That's not true. That would be true if radioactive substances decayed linearly, but they don't decay linearly, they decay exponentially, right? So that means that if a radioactive substance has a half-life of 5 years, then starting with 16 grams, there will be 8 grams left after 5 years. And then 4 grams, right? Half of 8 is 4. 4 grams left after 5 more years. So after 10 years, there will be 4 grams left. And then half of 4 is 2. So there will be 2 grams left after 5 more years, right? So after 15 years, there will be 2 grams left. And so forth. After 20 years, there will be a gram left. After 25 years, there will be half a gram left. Right, and so forth. So theoretically, there's always going to be some of the radioactive substance left over, right? That's important, especially when you're talking about radioactive dating, because you may think, well, how can they radioactively date something that's, you know, millions of years old when, you know, the half-life of the substance is only thousands of years old? Won't it all be gone in a couple thousand years? And the answer is no, right? There's always going to be some amount of the substance left over, theoretically. In reality, the radioactive substance will eventually all decay, but it takes longer than twice the half-life for that to happen. Okay, much longer. Okay. Another thing to point out is that the half-life, h, is not the same thing as the decay rate, k. All right? Or actually, I think the letter I've been using is r. I've been using r for the decay rate. So the half-life h is not the same thing as the decay rate, r. However, the two are related, right? So the half-life h of a substance undergoing exponential decay at a rate r is given by this formula. H is negative ln 2 over r, where r is your decay rate and h is your half-life. And here's a proof of that fact, right? It uses the same reasoning as we used before, right? We said if we want our final amount to be half of our initial amount, then we can just plug in 1/2 p naught in place of p in our exponential decay formula. And then the p naughts will cancel, and then you can take logarithms, right? Ln of 1/2 is the same thing as ln of 2 to the -1. And then we can apply the product rule or the power rule to bring that negative out in front. And that's where the negative ln 2 comes from. And then to solve for the half-life h, we divide by r. Okay. So, but I'm not going to go through these steps every single time. I'm just going to use this formula that we've developed now. So whenever I'm given something with half-life, I'm going to use this formula to figure out what the decay rate is. Okay. For example, 100 grams of strontium-90. It's been so long since I've taken chemistry, I have no idea if that's a real thing. It sounds kind of real, but then it also sounds like kryptonite a little bit. I don't know. Krypton is a real thing, though. Anyway, 100 grams of strontium-90 decayed to 66 grams in 15 years. So you're going to watch this and you're going to think, wow, Mr. Haywood's really pretty ignorant. And you're probably right when it comes to chemistry, that's for sure. I should do something about that. I should take a chemistry class or something. Anyway, 100 grams of strontium-90 decayed to 66 grams in 15 years. Find the half-life of strontium-90 to the nearest year. Okay. Well, in order to find the half-life, first we're going to need to find the decay rate. In order to find the decay rate, we're going to use our decay model, right? Our exponential decay model. We're going to say P equals P naught e to the RT. Okay? So we started with 100 grams and ended with 66 grams. It took 15 years for that to happen. So T is 15. And R we don't know, but we can solve for it, right? So, so I'm going to, well, so this is 66 equals 100 e to the 15r, and we want to solve for r. So I'm going to take natural log of both sides. Actually, before I do, maybe I'll divide by 100. So dividing both sides by 100, I would just move the decimal twice, right? I would get 0.66 equals e to the 15r. Now I'll take a logarithm. And then divide by 15, right? So r is ln of 0.66 divided by 15. I'm not going to bother to get an approximation for this yet because I want an exact answer. If I round this at this step, then I'm going to have rounding errors in my final work, and I don't want that. So, I'm not going to do that. Instead, I'm just going to use this exact answer, and I'm going to use it in my half-life formula, right? I'm going to say half-life is negative natural log of 2 divided by decay rate. So H is negative ln 2 divided by R. In other words, H is negative ln 2 divided by ln 0.66 over 15. Now, if you work that out, this big fraction bar is just a division sign. So you can flip this other thing over and multiply. H is negative 15 ln 2 over ln 0.66. There's my exact answer. Now, if I want a decimal approximation, I can pop that into my calculator and see about how much the half-life is. So negative 15 ln 2 divided by ln 0.66 is 25.022 approximately. So I guess 25 years would be the half-life, right? Now it makes sense that we're getting something bigger than 15 because it took 100 grams 15 years to decay to 66 grams, but half of 100 is 50, right? So so it makes sense that it's going to take longer than 15 years for 100 grams to decay down to 50 grams, right? So it'll actually take a little over 25 years for that to happen. But there you go. There's our half-life. Years. Okay. Oh, wait, I said to round it to the nearest year. Oh, okay. Well, so to the nearest year, it would be 25 years. 25 years. Okay, so that's that. Let's do another one. It says carbon-14 has a half-life of 5,700 years. If 60 grams of carbon-14 decays for 3,000 years, how much is left? Okay. So this time I'm going to work backwards from what I did on example 4 because I'm given the half-life and I need to find the decay rate so that I can use it to make this prediction. Okay. So I'm going to use my half-life formula again. But I'm going to use it to solve for the decay rate. All right. So I know that the half-life is 5,700. Solving for R, right? That's my decay rate. Now I'm going to use that decay rate to get my to make my prediction, right? To make the prediction, I'm going to use P equals P naught e to the RT. So I want to know what the final amount is going to be. If my initial amount is 60, my decay rate is negative ln2 divided by 5,700, and the time is 3,000 years. Let's see what I get. (60e to the negative ln2 divided by 5,700 times 3,000. Okay, so that comes out to about 41.660 grams. That's more than half, and that makes sense because the half-life is 5,700, and we're only interested in how much is left after 3,000 years. So, so that makes sense. All right, so that does it for 3.3. That'll take care of our discussion of exponential and logarithmic functions. So in 3.4, we'll start talking about trigonometric functions.